Thanks for the invitation. I'm very happy to be here at ODSC. I was in ODSC a few years ago, and I was in San Francisco, and it's a great conference. So very happy to be here. I have the chat right in front of me, so feel free. I have two chats in front of me, so feel free to ask questions in the chat. Also, feel free to ask questions in the live session. I'm right here. I put a post there. And yeah, so this is time is yours. So if we go in a different direction in a tangent, then it's even better. So I will, and if you don't mind telling me when I think I have half an hour, right?
Yes, 30
okay.
minutes.
Perfect. We'll probably do 25 and then 5 of questions. But as I said, I receive questions at any moment. So I'll tell you about reinforcement learning with human feedback. And the topics we're gonna see, and just to check, will you see my screen? It says topics, right? Okay,
yes.
Perfect. So I'm gonna teach a few things today. Time permitting, we're gonna very quick intro into large language models. I don't expect them knowledge of them, but if you have knowledge of how they work, that's fantastic. You for sure have played with ChatGPT and any Anthropic, Cohere, Gemini, any of those. They all work in the same way. So I'll tell you a bit about large language models, which we call transformers. Then not how to train them. How to train them is a topic for a different day. But imagine if they're trained, you're going to show you how to fine tune them with reinforcement learning with human feedback. So you will use humans to actually interact with the model and get that. The idea is to get the feedback of the human into the model as quickly and effectively as possible. So I'm going to give you a very quick intro to reinforcement learning, and then to PPO, which is proximal policy optimization. Is the reinforcement learning technique used to fine-tune large language models. Then we're going to go to direct preference optimization, which is a non-reinforcement learning way to fine-tune the models using the human feedback, and it actually proved to be more effective. So it's funny, I talked about reinforcement learning in my talk, and I'm going to end up with a non-reinforcement learning improvement to it, but it's still useful, right? I still uses the notions of reinforcement learning. So let me start with just a very brief intro / reminder of how large language model works. And when I think of a large language model transformer, I think of a transformer like Optimus Prime here. And the idea is that it generates texts, as we know. Something that blew my mind is that it generates text one word at a time. So it doesn't just plan what it's going to say and says an amazing essay. No, it just generates the next word. So if I say, for example, hello, how are you? It just comes up with doing the next word, just figures out that's the next word. If I say something like write a story, it doesn't start writing a story, it just starts thinking about a story. It says, how would a story start? Probably the word once. That's all, that's as far as it goes. And then how do you continue writing the story? Well, you put once back into the input and you go, okay, write a story once. And then it says, yeah, you probably want to say upon here. And it does this very quickly and repeatedly. Then you put in once upon, write a story once upon, and it says and continues writing the story one word at a time. What it really does is it finds probabilities for every word. So after everything, after an input like write a story once, it just goes through all the existing words. It's actually existing tokens, but small difference. Let's pretend they're words, all the existing words, and it outputs a probability for each one of the words. And as you can see, some of them have very low probabilities because they're probably not the next thing. And some of them, like once there or once upon, have high probabilities. And then it picks out of them, so that it doesn't answer always the same thing, but it answers different things every time, but that are very likely to be the right thing to say. So it picks upon, and then that's how it picks the next word. So this is very important because these think of these arrows as where's the next step the transformer is gonna take. And it has a probability for each one of the steps. And then it picks a step with high probability, which is the next word, which is upon. So how how to train transformer models? Well, it's a humongous neural network with a bunch of boosters on the side, like attention and embeddings and certain things. But imagine a humongous neural network, a humongous machine learning model. And the way you train it first is to just go through the entire internet, just the entire thing, like just read all of it, picking up, so it starts knowing how to pick up the next word in a smart way. But once it's done with that, we're not done yet, because it still needs to know how to answer questions. It still needs to know how to follow orders that are not what the internet tells you, right? The internet is not a repository of questions and answers. So you can, after that, the expensive part is to put a lot of curated data sets, put a lot of question answer data sets of with facts and things like that, and then you train it like that. And then it's still not done, right? That's not the end of the story. Once you have your model, once you have your model, then you still wanna do some fine tuning. By the way, I see a question there by Etienne, so thank you for the questions. Put them in there, and I will break at some points and answer questions. So thanks for the questions. Feel free to put them either on the chat or on the live. So that's not the end of the story, because we still want to fine tune them. So we're gonna get a lot of humans to help us out. How do they help us out? Well, let's say we ask a question like, what color is the sky? And let's say that the model gives us 3 probabilities, for example, three possible answers. One is blue, one is red, and the other one is banana. So we need a human to tell us which one was better. And so the human says, well, the best one was blue. And now the point of reinforcement learning with human feedback is to come in and infuse this to the model. All right. So now I'm going to go to guide to reinforcement learning, but I'm going to answer a quick question here by Etienne, because it's about LLMs. It says, how does outputting probabilities work if you ask to write a summary of a given text? That's a great question, Etienne. So if you, for example, if I have a text and I say, write a summary of the text, it still writes it one word at a time. So it starts with yes. Then the next question is, of course, like the next, it starts writing, but it always looks back. So it always looks, it can only go one word to the future, but many words to the past. So every time it reads the entire text, because your question is write a summary of the text, and then part of the input is the entire text. So it always reads it, but it still writes the summary one word at a time. Okay. If you have any follow-up questions, feel free. So let me give you a quick intro on reinforcement learning, and I have some questions for you. So I'm wondering if you can answer, if you can type the answer in the chat, that's fantastic. If not, don't worry, I'll answer them. But if you'd like to be part of the of this, then that would be lovely. So we start with a grid world, and a grid world is a game where I have a bunch of squares in a grid, and I have an agent. The agent is the little orange circle over here. And I have some rewards that could be positive or negative. I have, let's say, a lot of money here, a lot of money here, and a dragon here. So I want to get to the money and avoid the dragon. And let's say that we have points. So this money is +5, this money is +4, and the dragon is -1 because I don't want to get killed. So I have some barriers here that I cannot block, that I cannot cross. And the idea is to walk around the grid, to tell the agent how to walk and to get as many points as possible. So here I got 4 points, but the idea is to have hopefully get +5. So there are something called states, which is every single place where the agent could be. So it could be in the red, in the dragon, in the money, or anywhere else around, except for the barriers. Those are the states. Then we also have actions, which are everything the agent could do. So I like to imagine actions like a supermarket during COVID, where there's arrows in the floor and they say you can walk in this direction, not backwards, and you can choose to walk in the directions of the arrows or not, but you cannot do anything that the actions don't allow to, right? So something like this could be an action where you can go in any direction. However, a better set of actions would be this, where you're kind of not crashing against the walls, right? That would just be like a small improvement for this. And so those are the actions. And now let's add a difficulty. It costs one point to move. It costs one euro to move one spot. So if I'm here, then I can assume that if I'm in this spot here, I have 4 points, because the best I can do is to get to the 5. And that's the value, right? So I have a quiz. I don't know if it's easy for you to answer on the chat, but if you can, what's the best I can do from this spot over here? How many points? What's the value? Who can help me out? Someone's typing. Rafael's typing. Let's see. All right, since timing is short, I will answer my own questions, but feel free to. Oh, I see people are typing, so maybe I'll wait. 2 points, correct. Jordan got it. Jinwa got it. Etienne got it. Chandini almost. Can do 3, but actually 2 is better. Jake, Rafael got it. Yeah, it's actually 2, because if I do this, then I can get 2, 4, 4, 3, and 2. So the 2 is the best I can do from that spot. Now, in the interest of time, I will answer the next one, but feel free to put the answer in the chat. What is the best I can do from this spot over here? So I could walk all the way to the 5, right? And get minus 4 points, but it's actually better to walk all the way to the 4 and get 2 points. So from here, the best I can do is 2, because the strategy is to walk into the 4. And if I'm here, I'd rather walk into the -1 than lose a lot of points to get to the to get to the +4 or the +5. So the values are basically, I can propagate them out of the points slowly, and I can get that these are the values. So if I'm in any of those boxes, the best I can do is that point. So if I'm here, the best I can do is to walk into the -1 and get -2 by paying one euro. So those are the values. And now I have something else. The values, if it was free to move, will be all 5, right? If it didn't cost 1 euro to move, it would all be 5, because wherever I am, I can walk into a 5, right? Now I have something called a policy. So here's the policy. If it was free to move, if it didn't cost 1 euro to move, my best policy would be to kind of try to get to the 5 and not get to the 4 and not get to the 1. So if I remove the arrows that get to the 4 and that get to the -1, then I have a perfectly good policy. It says if you walk around those arrows, one day eventually you'll get to the 5 and win. If it costs 1 euro to move, then what's the best place to move? Well, you can use the values, right? If I always make sure I'm moving towards a value that adds 1, or that's the biggest possible value around me, then I'm good, right? If I'm in this 1, the best thing I can do is to either move to this 2 or to this 2. So let's pick this 2. If I'm at this 2, I can move to the 3 or to the 3. Let's move to the 3, and so on and so forth. So if I pretty much put an arrow from each number to the biggest number around them, I have a perfectly good policy, right? Because I'm walking, adding the most I can. So if I'm here and I follow the arrows in whatever way I want, I guarantee to do as best as possible. All right. So I have, normally this is a deterministic policy that tells me an exact thing to do. Sometimes I have options, but they get me to the same place. What I want is a stochastic policy that gives me probabilities, okay? And so a strong arrow is a strong probability, and a little arrow is a little probability. But the idea is that I have high probabilities to get to the big values and low probabilities to get to the small values. That's a stochastic policy, and we want that instead of a deterministic policy, and I'll tell you more in a minute. But like large language models are a stochastic policy, right? Because picking the next word is not deterministic. ChatGPT doesn't want to give you the same answer every time. It wants to change it around a bit. So stochastic policies tend to be better for training and for outputting answers for the most part. So now we get to neural networks, because in reality, if we do the values and then we get the policy, we have completely answered this question, right? I have completely solved this game by either giving you all the values, all the numbers you can get, or giving you the policy, because now you win at this game no matter what. However, the game could be much bigger, right? Like the game could be thousands by 1,000 or millions by millions or infinitely many states. And then it's really hard for me to go around, because I need to in order to find the values on the policy, I need to play this game many times and start adjusting them, and I can't walk in a huge space repeatedly. Sometimes there's infinitely many spots, right? If I'm training a robot hand to work, that's reinforcement learning, and I have infinitely many positions of the hand. I can't come up with a value for all of them. I can't come up with a policy for all of them. I need something, which is a neural network. So what happens with a neural network? Imagine that you have a value for this, and you figure out the value for this box, okay? And likely the values for the box around them are not very far from it, right? Like if this is a 4, this is either a 3.9 or 4.1, something similar, right? And the box around them are also similar. Same way, if this is a negative number, these are similar negative numbers, right? And so that hints of a neural network, because I could come up with a neural network and input the coordinates of the box and output the value. It's not going to be the value, but it's going to be something close to the value, okay? So I can come up with something called the value neural network, and the value neural network is going to approximate the values. If I input the state, it's going to learn to say, hey, your value is probably something like close to this. So that's the value neural network. And I can also have a policy neural network, because my policy here, if I figure out the policy for this one, it's close to the policy for the neighbors and for the neighbors and for the neighbors. So I can come up with a policy neural network that, given the input conditions, given the coordinates, it spits out now it's 4 numbers, right? Now it's 4 numbers, because the 4 numbers are the probabilities of the 4 directions I could go. It could output more stuff, right? If I have infinite directions I could go, it outputs a probability distribution, but it outputs as many actions as I need to make. So now we have, for example, here I should probably go up, so it's a higher probability to go up than to go down. So now I don't have my values, because there's too many for me to calculate, but I have a value neural network that gives me something pretty close. And that if I modify it a bit, it changes all the values. So it's good for me because I can apply it anywhere, right? And I don't have the policies. Now I have a policy neural network, which gives me a stochastic policy. I prefer a stochastic policy than a deterministic policy, because as I train the neural network, a deterministic policy doesn't move around too much, and it kind of picks, if it picks a path, it sticks with that path, whereas the stochastic one will always allow me to explore and to exploit, because it says, you know, you're likely to do well in this area, so I'm going to take you more in this area, but one day I'm going to take you in a path through these alleys and stuff, and you'll be able to find out more about those places. So stochastic policy is much better for training than a deterministic policy. Okay, so we're about halfway, right? About 10 minutes. Now we have all the players. Let me tell you what RLHF is: reinforcement learning with human feedback. The idea is that we want to play a game where the agent is the LLM that's talking, and the actions are given by that, and the values are given by the human. So when the LLM, when the transformer says what color is, we put a prompt that says what color is the sky, and the transformer answers 3 questions: blue, red, and banana. Then a human comes in and says, hey, I think you want to say blue. So I'm going to click on that one. As a matter of fact, what we want to do is to make the agent play a game and with reinforcement learning, and have the values come from the human. So what the human does is, so each state in the agent is a sentence, okay? Each state in the agent is a piece of text, and moving around is adding a word. So when you're here at what color is the sky, that's where the agent is. Then the 3 words you could add are red, blue, and banana. And the human won't just pick, it would actually rank things and give them scores. So 3, 2, 1, for example, 3 for the good solution, 2 for the so-so solution, and 1 for the bad solution. And each one would be the value of that corresponding state, okay? And now what we have to do is to train a value neural network to guess these values. So the point of the value neural network is to guess what the human's gonna say. We train a neural network to guess what the human's gonna say. And then we also have an action, a policy neural network that's gonna train what the next action will be. And that's the transformer, because that's the one that picks the probabilities, right? Like the policy neural network is ChatGPT, is the language model that when it's given some text, it adds the next word. Okay, so now we have our two neural networks, and this doesn't have to work with only one word. We can actually come up with a full response. I can say roses are red, and then the transformer will output roses are red, violets are blue, or roses are red, violets are humans too, or roses are red because they like ketchup. This is the 3 directions the LLM could go. It outputs those 3, and a human says, you know what, roses are red, violets are blue gets 3 points. The other one gets 2 points, and this one gets 1 point because it's the worst one. So the point is to train the neural network to guess actions that are big for the good answer, that are medium for the medium answer, and small for the bad answer. And so you train the value neural network to guess these values, and you train a policy neural network to guess the actions. That's the idea. If you remember one thing, just remember this: you're playing a game with where the LLM has to play the game, and the game is, the way to win the game is to satisfy the human. So to give the human as high scores as possible, to have the human give you as high scores as possible. Obviously, it's not a grid, right? Talking is not a grid. I don't have 3 or 4 possible answers for every sentence. I have many more. So this is a huge high dimensional space where there's an arrow between each sentence and the sentence with 1 extra word. So for example, hello, how are you, and hello, how are you good have an arrow between them, and it's a strong one because this is likely to be the next word. Hello, how are you, banana has a very tiny arrow because that's probably not the next word in that sentence. And the idea is to teach the LLM to walk around this space. So here's a good answer. What color is the sky? The sky is blue. Those arrows are pretty strong, whereas the arrows here for what color is the sky, banana, purple, monkey, dishwasher are pretty weak because I don't want to go in that direction. So the idea is to train the agent to play this game, to give it a good policy to walk around making sense in the sentence, and a good policy is the LLM, right? That tells you what word comes next. Feel free to ask any questions in the in the chat. I see one question, and I will answer at the end. It makes sense. So yeah, the idea is to have the value neural network guessing the output of the human, and to have the policy neural network guessing what these arrows be, so that the transformer can kind of walk around. I think I have about 5 minutes, so I think I have time to tell you the loss functions of the 2 neural networks, and then I'll give you an idea of what DPO is. But feel free to stop me if I go over. So let's do training the value neural network. How do we train the value neural network? So remember, we have 2 neural networks: the one that calculates the values or approximate the values, and the policy neural network that approximates the policy. So I'm going to tell you how to train the value neural network. The value neural network gets trained with this loss function: expected value of blah, blah, blah minus blah squared. What are those? Well, here's what happens, okay? Imagine that I'm training the neural network, and these are the values I have. They're sloppy. They're not very good because I'm in the middle of an iteration. Doesn't matter. I'm going to do one step. One step means I'm going to walk around until I finish, okay? So until I get an answer from a human, or until I reach a point. And then these are my values along the path. How do I get this path? Using the policy neural network that I have, which is also not that great. I'm still training it, right? I'm training it at the same time, but I work with what I have. And so now I look at what the actual values would be, because for that little path, I can actually calculate the values and back propagate. Remember that if I get to a 5 here, I'm back in the grid example, but this can also, you can imagine it with an LLM. And the values are 4, 3, 2, 1, 0, and -1. So I want to compare what the network gave me with what the values were. How do you compare? Well, you subtract them and you square, right? That's a typical AI machine learning trick. What I want to do is I take the difference of the squares, I average it out because I want to average over the entire path, and 3.36 is my loss. So I want to make this number as small as possible. Why do I want to make it as small as possible? Well, because if I make this number as small as possible, then the actual values, the value neural network is going to output as close to the values as possible. So here is my, you use this to train the value neural network. And what you do is you do this with many paths, right? I do this with this path, and I take another path, and I fix it, and I take another path. And if I do this many times, I don't have to walk over the entire grid to get something pretty good. If I walk around as much as I can, I get a neural network that gives me something pretty good. So the formula for the loss function is this one, because it's here, right? The expected value is the average. We divide by 6. This v theta of st is this. Theta is the st is the states, and theta is my parameters, and v is the value. These RT are the actual rewards, the values, and this square is here. So the formula, as ugly as it looks like, it's really just telling me how different, how far is my values from the values the neural network gives me. I'm going to quickly tell you, this is used to train the value neural network. I'm going to quickly tell you how to train the policy neural network, and I'm going to stop in 3 minutes. Should I stop in 3 or 5? Let me know.
We have 5-6 more minutes if you want.
Okay, let's do 5-6 so I can actually do the surrogate, and then I can tell you a bit about DPO, and then we wrap up. I see some really good questions, so I'm gonna, yeah, I'm excited about answering these good questions. So we have the 2 neural networks. Now I'm gonna tell you how to train the policy neural network. This is a little trickier, but it's fun. Check it out. So what I wanna do, this is the policy, the loss for the policy, which looks ugly, right? But it's not that bad. I do the exact same thing, right? I'm here, and I take a path, and my path, let's say, goes to 5. How do I pick this path? With the policy neural network. So I have my value neural network to give me some values, my policy neural network to give me some arrows. They're not great, but I can work with them. And then what I do is I compare it to the actual value. So I do the exact same thing as before, basically, except now I'm not gonna update the values. I'm gonna update the policy. So how do I update the policy? Well, let's pick one of these values. For example, the 4. Yeah. And I'm gonna go here, and I'm gonna say this was 1.2, and I want it to be a 4. So the value should go up, but the policy should also go up, because I'm not walking into a 1.2, I'm walking into a 4. I should increase this policy, right? So I tell the neural network to increase this policy, and my gain is 4 minus 1.2, and my probabilities here. So this is the function that I want to increase. Okay, so I wanna it's a positive number, so I want to increase my probability. If it was a negative, because I have a smaller number than I should, then I would decrease it, right? So here's the gain, right? Like here is the probability, and here is the gain. And what is this? So this is a weird thing. Why am I dividing by the old probability? Let me tell you a bit. I see it as an impulse. So an impulse works in the following way. Let's say I have a kid running, and the kid, let's say the idea is that if the kid is running fast and I push him, he goes faster. But if the kid is running in the opposite direction and I push him, he goes slower. Physics, right? So if the kid is going at 10 and I push him with a force towards the kid, then now he's going at 20. Whereas if the kid is running towards me and I push him, then it's not going to go 20, but it's going to go at 5, because I have to take the impulse. And that's what we're going to do with the model, right? If the model's been growing, probabilities, I grow it more. But if they're decreasing and I want them to grow, they grow slower. So basically, that's the impulse. And so basically, if the probability has been growing and I get a gain that's positive, then I grow it even more. But if it's decreasing and I have a gain that's positive, then I grow it very little. Because I haven't, if the impulse matches the gain, I grow the probability a lot. If the impulse is opposite to the gain, then I don't grow the probability that much. And that also works going down, right? If the gain is negative, if the probability is growing, I don't grow it that much. And if the gain is positive, if the probability is decreasing, if the gain is negative, the probability is decreasing, I decrease it more. So let's do a scenario. Let's say I'm in iteration 100, and my probability is 0.4, but my gain is very large, which means that my value is 10 more than what I expected. So I need to increase this probability. How much do I increase it? Well, if iteration 99, the probability was going from small to big, then I want to make it much bigger. But if the iteration 99, it was going from big to small, then I don't want to make it that big. So you see, here it went from 0.2 to 0.4, so I want to go all the way to 0.8. Whereas here it went from 8 to 0.4, and I want to grow it, but not so much because it's kind of going in the wrong direction. I want to grow with impulse. So PPO is basically growing it with impulse. So if it went down, I don't want it to go up that much. And so what I do for my loss function is my surrogate objective function is I take the probability, I divide it by the previous one, and I multiply it by the gain. So here I get a big number, whereas here, if I divide it by the previous one, I get a small number because this is a big number. So basically, if iteration 99 tells me a lot about how to move iteration 101. If this is not clear, feel free to ask any questions. But the idea is that I wanna grow these probabilities when they have to grow, but with impulse. And that's why I pick, for example, probability of iteration 99. This is the probability of iteration 100. This is 99, and this is the gain. And that's the policy that I use to train my policy neural network. I'm not going to get very far with DPO. This is a little more technical, and I have about 1 minute. So I'm just going to tell you that a technique that's really good called this direct preference optimization was discovered recently in a great paper. This is the paper, Language Strictly a Reward Model, which bypasses the reinforcement learning part and trains a neural network directly. And so basically, it takes this is the loss function of the neural network. It's over here. It only uses the probability, so it completely bypasses the reward model. And how does it bypasses it? Well, because it originally has this formula over here. And this formula over here basically has the reward model and the policy model. I'm gonna skip over a little bit. Oh, actually, I'm gonna tell you this. This part over here maximizes the rewards. So your loss function has to maximize the rewards, and therefore picking the good answer, right? If it's once upon a time or banana, it wants to pick time. So this part here maximizes the rewards, and this part here makes sure the model doesn't change too drastically. So if I was given a model, reference model, and I want to fine tune it, I don't want to change it too much. I want to change it very little. So this part over here, DKL, is the difference between these two, the KL divergence. And so this part makes sure that my model doesn't change too much from one iteration to another. And so if I'm maximizing the rewards and minimizing the difference between the models, then I get, sorry, I'm just gonna scroll up a bit here. I was too optimistic. I had a lot of more material than that I wanted, but the idea is that you get this formula over here. So using mathematical manipulation. So moral is you can train a neural network with a complicated loss function that bypasses the reinforcement learning. And I think with that, I will stop. I had a few more things, yada, yada, blah, blah, blah. Before I stop, I want to tell you, I have a YouTube channel called Serrano Academy where I have these videos. So these videos are, there's 2 hours of material, 4 videos of half an hour where I talk about reinforcement learning, PPO, RLHF, and direct policy optimization. So if you want to take, this is the trailer, if you want to do the whole movie, feel free to check out the channel, Serrano.academy. I'm going to put the link here in the chat, and then all the details will be there. So thank you. Sorry, I went a couple of minutes over, and I think I can answer questions. But if you want to, I can answer the one.
If you want to choose one question, and then all the other questions you can type the answers if you want.
Oh, okay. Did you choose one? I feel like. Do you have a preference? I can read them, but if you have a preference, I can answer that one.
Your preference, your choice.
Well, I'm gonna answer whatever I know. Yikes! I will answer them in I'm gonna answer a couple. Just conceptual question. What is your opinion on RL by AI feedback? Do you think it can beat RLHF in terms of scalability and tuning? That's a great question. I feel like you can because you're training the value network to guess what the human would do. So if you have a good one, then you'll be able to not only use a human, but train a model that mimics the human and scale. It has more scalability. I'm gonna answer another one. The one that Anastasia surfaced, which is how do LLMs work in different disciplines like finance, health? They work great because they basically answer questions for you. But something that I would do with something like health, for example, I would not trust an LLM with health decisions, right? I'd be like, hey, I have this, help me out. But I would use RAG. So RAG is retrieval augmented generation. And it says before talking, search in Google or search in Wikipedia or search in all this database of documents and answer from there. That's more trustable for health and for law or for anything that is sensitive information. Definitely I would use RAG. So if you use, now the research is in tools. You can use the calculator if it has a math question, you can use the Google search, it can use different things. So an LLM with good tool usage can be used for anything. I can answer the rest of the chat, so I think we're about time, right?